Hello everyone. Today we'll talk about chapter 1 of the book. It's the chapter about linear regression with one predictor. Okay. So I have some typed up notes for this, and that's the lecture part 3. Okay. So again, so what I would recommend at the end of this lecture is that you go and read chapter 1 of the book very thoroughly. Okay. So, what we want to study in this class, the motivation for the goal in this class is to study relationship between random variables. Okay, so let's say you have two random variables x and y, and we want to study how these random variables are related. Okay, specifically, we want to study how y depends on x. Okay, in this class x and y have specific notations, and when we always study how y depends on x. Okay, so for example, like what will happen if x change, what will happen to y if x changes. Okay, and the way we do that, the way we will answer this question is by collecting data. So generally, we will go and ask n people or n objects, and they compute their xi's, their x's, and the corresponding y's. Okay. So x is called the predictor, or the independent random variable, and y is called dependent. So that's the response random variable. So like, let's think about this. Let's think of it this way. So x could be the dosage of a drug, and y is the amount of relief in pain. Okay. So, the question is, we want to study how does the dosage affect the relief in pain. So like, what if you took 1 ibuprofen or 2 ibuprofen or 3 ibuprofen or no ibuprofen, and y is the amount of pain you are in, right? So you can see clearly that x, once x is, you can choose x, but once you have fixed x, y depends on the value of x, right? So that's why it's called the dependent variable, because y depends on x, right? The value of y depends on x. But so if you wanted to study the relationship between the dosage and the amount of pain you are in, what you will do is you will assign people, you will go to people and you will give them 0 or 1 or 2 or 3 or 4 ibuprofens when they are in pain, and ask them how much reduction in pain they got, right? It's very similar to the blood alcohol content data we saw before, right? And so what we want to understand is how does the relationship between x and y work. So there are two kinds of relationships that generally exist in nature. One is called the deterministic relationship, and the other is called statistical relationship. Okay, so what is the deterministic relationship? Deterministic relationship means that x determines y. If you know x and you knew the formula of how x and y are related, you know exactly what y is, right? Statistical, so this is saying that you know exactly what that formula is. Statistical relationship is more complicated. There is randomness. in the value of y. Okay, at least maybe there is randomness, or there could be something else that causes change in y and when x is fixed. Okay, so an example of deterministic relationship is this here. So here is the so suppose you run a toy store, okay, and where you sell drones, and each so the goal is to find out how much is your income, okay. So you know when you like sign up for a exclusive store, maybe the drones, so it turns out that the drone company pays you $500 a month for expenses, and each drone you sell, you make each drone you sell, you make $50, okay. So you earn $500 every month just for selling that brand's drone, and each drone you sell, you make $50 per drone. The question is how much money do you earn before expenses, right? So on day one, suppose you sold 75 units. So here, sorry, x is the independent random variable and y is the dependent random variable. Y depends on x. So on the first day, suppose you sold 75 drones, then the profit is $500 that you earned no matter what, plus 75 times 50. And if you sold one drone, then that's the profit, okay. And if you since the profit is exactly determined by the units sold, this is a deterministic relationship. All right, this is a mathematical formula that is exact, okay. So let's talk about an example that is a statistical relationship. So in this example, it's a data set from 1920s, and what they had done is they had gone and tried to figure out the braking capabilities of 50 different cars, okay. And what did they do is, they had 50 different cars, and each car they drove at a different speed, and then they tried to see how long it and then they applied the brakes, and then they wanted to see how long did it take for the car to stop, like how far did it travel before it stopped, okay. So so they drove the first car at 4 units of speed, and then it took them 2 feet to stop. So like let's say they drove the car at 4 meters per second, and then it took them 2 feet to stop. And then they drove another car at the same speed, and when they applied the brakes, it took a little bit longer to stop. And when they drove another car at 7 and kept increasing the speed, and like saw how fast, or kept changing the speed over here, and then saw how long did it take the cars to stop, okay. So, and this relationship is not deterministic, because if you know x, you don't know what y is, right? So like there are two cars that have the same x, but they have different y's, right? In a deterministic relationship like here, if you know x, you know y. In a statistical relationship, if you know x, you don't necessarily know y, okay. There is still, y can still change for if two people have the same x, they do not need, this does not mean they will have the same y, okay. In a deterministic relationship, two objects or people have the same x, then they will have the same y. But in a statistical relationship, if two people have the same x, they might have different y's. Okay, so so why is this what's happening here? I mean, if you wanted to think about it here, it could be like, there are two different cars. Some cars have better brakes than other cars. Some cars are like slower, and some cars like are slow to stop. Like a truck does not take the same distance to stop than like a sports car, right? A sports car has a better brake, and so it turns out that the stopping distance is not exactly determined by x, but might require other factors, like how big is the truck, how good are the brakes, or how slippery is the road. Maybe these cars were driven on different roads, or how slick did it rain yesterday. So there are other factors that affect the value of y other than x, right? In here, we know exactly what affects the value of y in x. Okay. And then there is randomness, right? Like, so if it rained yesterday or if it didn't rain yesterday, the car will take longer and shorter to stop in this data set, right? And what we want to understand is how can we like figure out the underlying relationship even with all this randomness, even with things that are changing. Okay? So let me, so of course, if you, let me try to see. Yeah. So let's try to plot these two data sets. Okay. So let's try to, so as I said in the first class, in the earlier classes, if you want to analyze the data, the first step is to plot them. So let's try to plot the data in table 1 and table 2. Okay. Let's try to plot both the data in table 1 and table 2. So this is the plot for table 1 and this is the plot for table 2. Okay. So here we have the number of units sold. Something wrong somewhere. Right. So this is the number of units sold, and you can see if you look at them that there is exactly a straight line. Come on. There is exactly a straight line going through these pies. Right? That's because we know the deterministic relationship. If you tell me x, then y was 500 plus 50 times x. Okay? So when I write a straight line, like this, it means 500 is the y intercept, and x 50 is the slope. Right? Y equals to mx plus c. You remember that equation? M is the slope, c is the intercept. Okay. So since in a deterministic relationship, the relationship between y and x are exactly the same and they fall exactly on a straight line, right? Every data point falls on the line. But when I plotted the table, the car's data, where on the x-axis I have the speed, this is the x variable, and on the y-axis I have the variable y. You see, there are cars that have the same speed but have different stopping distances, right? That's because, as I said, there can be other factors affecting the value of y, right? So the scattering of points, even for the same axis, is a telltale sign of a statistical relationship, right? As if you remember this, each point on this scatter plot here, so this is the statistical relationship. Each point on the scatter plot, so the whole thing is called scatter plots. Each point on the scatter plot is called a trial. Or data point. Okay. So let's talk about another example of statistical relationships. In this sphere, I have plotted the relationship between age and steroid in the plasma of 27 healthy females between 8 and 25-year-old women. Okay, so I have 27 women between 8 and 25. I look at them and I compute. I look at the blood and I measure their steroid levels in their blood. Okay, and I plot them. Forget the line for a second, forget the solid line for a second, but the dots represent the scatter plot. Okay, so here you see that the relationship between y and x is not deterministic, because the people can have the same value of x almost and have multiple values of y, right? And they don't fall on a curve, right? The scatter plots in a statistical relationship does not fall on a curve. If all your data points fit in a very nice simple curve, then it just basically means that the data set is that the relationship is deterministic. And the scatter plots don't fall on a curve if the data has a statistical relationship. And here, this black line denotes the trend of x and y's relationship. Okay, so what does it mean? It means that it's showing that in the beginning, when x increases, the steroid level increases, and it flattens out around 20, and then it goes down, right? So the steroid levels goes up and then goes down after 20. Okay, and so in a deterministic relationship, we can figure out the curve that relates x and y, and that would be exact. In a statistical relationship, since x and y are not exactly related, what we are generally interested in is this trend, and this trend is called the regression curve. Okay, so we will define this curve more carefully soon. But what we are trying to answer here is, what we are trying to do here is that since that we can't say y equals to f of x for some function of x, because we can't say this because it's a statistical relationship and not a deterministic relationship. And if it was a deterministic relationship, this would be true. But we can't say that. But we want to, since we can't say that, we're trying to find a trend that approximates this relationship well. Okay. So a way to understand statistical relationship is through this curve here. So let's look at another data. So the data is on on the x-axis we have the evaluation at the mid-year, and on the y-axis we have year-end evaluations. Okay, and we want to see how does how is the can we like the goal is to understand like how the year-end evaluations and mid-year evaluations relate to each other. Okay, and of course, like if you know your someone's mid-year evaluation, you have an idea of what their year-end evaluation will be. But they are not going to be exact. Some people will have a little bit larger, a little bit better year-end evaluations, and some people will have a little bit lower year-end evaluations. It's like you do, you are in the 50th percentile in the midterm doesn't mean you will be in the 50th percentile in the final, right? So you might be 60th percentile, you might be 40th percentile. So, but if you are overall doing well in the mid-year, it's probably likely that you're doing overall well in the year end, right? And so what we see here is that the relationship between clearly x and y is not deterministic. There is a trend in the relationship between x and y. Okay, and in this class we will break the relationship between y and x into two parts. The first part is called the regression curve. The second part is the error around the curve. So let me write this better. Okay. Okay. So the error. So there is a regression curve. That's the regression curve, right? Go back. Okay. Go back. Let's see if I can make this a little bit narrower. So that's the regression curve, okay? But every point does not lie on the regression curve. There is a randomness around the regression curve, right? Some people, so what it means is that if your x is, if your mid-year evaluation is 50, it's very likely that your year-end evaluation should be 50 or around 50. Some people will have higher evaluations and some people will have lower evaluations. And those that change from 50 is called the error, right? So if I go back to this example here, right, this how far you are off the line is called the error. So the length of these lines. So this is the error here. For this point here, the error is small. For this point here, the error is So for this point here, the error is small. For this point, the error is this guy, the length error. Okay. Maybe I should erase this and write it properly. This is the error. Okay. For this guy here, the error is small. Again, for this guy, the error is this. The error is how far it is off the regression line. Okay, or the regression curve. So that's a very standard notation we'll use, and we will use this again and again. Okay, so it just turns out a way to understand statistical relationship is to figure out this trend component and this error component and write down the relationship between x and y through this. So y is the value of the regression curve at x plus the error. That would define the value of y. Okay, So this is deterministic. This is the deterministic component. Okay, so this is the deterministic component of the statistical relationship, and this is the random component. Okay, so if I gave you a y and x and I told you that they have a deterministic relationship, you will try to compute this function. You will try to compute this line, right? But if I give you a statistical relationship, what we can do best is try to compute this trend, or try to compute the regression curve here. Okay, or try to compute the regression curve. After that, we can't really do anything more because the errors are random and it's hard to talk about them, right? So what can happen? What kind of relationships can x and y have? So the regression for statistical relationship, the only thing we can control is this is the deterministic part of it, or the regression curve. So the regression curve can be a straight line or can be a curve, right? Here the regression is a curvilinear function, right? It's like almost a quadratic function or like a parabola. But and in some cases the regression function can be more. It can be like a sine curve or exponential curve or so forth, right? And once you are at the regression curve, you might go up, you might go down lower, or it's like how the y's vary around the regression curve can also change, right? So in this class we will basically study very simple regression curves. Okay, so in this class we will focus In fact, we'll focus on the simplest regression curve. We'll focus on linear regression curves. We will, in fact, so the question is, why should we study that? Linear regression curves seems very specific and very narrow. We have so many different possible curves, right? We can have like sine, cosine, like exponential or quadratic. And why should we study linear curves? It turns out linear curves approximate things very well. So let's go back to this example here. Okay, if I'm interested in studying this, what I can do is I can be like, so I see that the age relationship between years and steroid levels is not linear. But what if I wanted to study from, instead of for girls of age 8 to 25, what if I focused on girls from age to 8 to 18, right? So this is 18, this is 88, and then I see that this relationship can be pretty well approximated by a line, right? This curve is pretty close to a line. So what it turns out to be is that if you focus on a small interval of x's, all relationships or all functions look like straight lines. And that's the beauty behind, that's the real intention of why we study only linear regression curves. Okay, so when I say linear regression, I basically mean I want to study a statistical relationship where the regression curve is linear. Okay, so if I had a curve so if I had this bold line, which is the true regression curve, I can even though it's not linear, I can approximate it well by this dashed linear line. And same is true here. So here the bold line again is the true curve, right? So the bold line is the true regression curve, and clearly it's not linear, it's wavy, it changes. But if I split the data into two parts, here and here, then I see that a line fits well here, a line fits well here, and a line fits well here. So I can split the data and I can fit two linear functions. Instead of trying to estimate this really complicated curve, I can try to find lines. And lines are the easiest objects, right? Because to know a line, I need to know only two things, slope and intercept. But if I want to compute a function that's very complicated, then I need many things, okay? So we focus on lines, on linear regression. Again, what is linear regression? Linear regression is the regression, is the relationship under which the relationship between x and y follows the regression curve that's linear. So linear regression means where a relationship where the regression curve is linear. Okay, so instead of saying relationship where instead of saying relationship where regression curve is linear, we're just going to say linear regression. Okay, and the point is, the reason we want to do this is like that linear regressions are the reason we want to study linear regression is that one, lines have a simple formula, just need two things, slope and intercept. Two, lines approximate curves well when in a narrow band of data. So if we have a very complicated data set, we can split the data set into many little parts and fit like linear lines to each part. Okay, and we can say, okay, if x is between 1 and 7, we use this line to figure out what y is, and if x is line between 7 and 20, we use this other line to figure out what x is. So you can fit this line, a line here and a line here, and predict based on that. Okay. So the question is, why do we care? Why do we care about knowing the relationship between x and y? The question is, why regression? So there are three reasons we study regression. Three main reasons of studying regression. One is description, the other is control, and the third is prediction. So what does it mean to be talking about description? So the description is talking about like we have a phenomenon in front of us, and it's a general it's a nature of, like, you know, it's how this is how curiosity works, is you want to understand how x and y are related, and regression provides us a way to quantify that. If they were deterministic, we could plot the function, we could just compute the function, but since they're not deterministic, we can't see how exactly they're related. So but we can try to understand them and approximate them by a regression curve. Okay. So so let's talk about an example here for this. Example for one is, so I think I missed one thing here, is that in this, until now, we have been studying the relationship between one x and a y, right? So x was the dosage, or x was the age, and x was the x was the number of beers someone drank. But it might sometimes make sense to have multiple x's. So instead of like having only the blood alcohol content, it might be more relevant to include blood alcohol content and the weight of someone before when I'm trying to figure out what their sorry when I'm trying to figure out what someone's blood alcohol content is. In addition to including the number of beers they had, maybe I should include age, because age provides a way to like control, provides more information about the person. Weight provides more information about the person. So if I wanted to study the relationship between the blood alcohol content of a person, I can use the number of beers they had, but I can also use their weight, their age, and their sex to understand the blood alcohol content better, right? So sometimes in regression we will talk about having multiple covariates, and each of these are covariates, right? And this is still the predictor, or these are covariates or predictors, and this is the dependent random variable. RV is the random variable, dependent random variable, or the response. Okay. So just to make our life simple, because we can plot when x is just a single thing, or when x is just one variable, then we can plot a scatter plot like here. We will focus on simple regression where the covariate is only one variable. So let's talk about an example where the data set and the regression model serves the descriptive purpose of a descriptive purpose. So the example that we're interested in is this tractor purchase data set, where for each region, there are many territories, and for each territory we know how many tractors are sold. Okay, since tractors can have different horsepower, so we'll talk about the total horsepowers of all the tractors in that region. Okay, so that's going to be our response: total horsepower of all tractors. And the covariates that we'll use to predict this, or to understand why, has many covariates. There are like 9 covariates in that study. The one that include age of tractors, number of farms in the region, quantity of crops, and so forth. And there's like 6 more variables. Okay, so the idea is, if we how are these covariates, how do they describe, or how can we use that to understand, how can we understand the relationship between these covariates and the covariate that is that is on the response, that is the total number of horsepowers for the tractors. Okay, so if we understand this, it will help us understand how tractors are sold, or how many tractors are sold in this area. So the goal is to understand describe the relationship between these two variables. Okay, let's talk about an example where the goal of regression is control. Okay, so this is this is an example here, is that so there are you have a bank or a finance chain. There are 67 branches for the chain. Okay, the response that we are interested in is the cost of operating a branch. Okay, for the last year. And the covariates we have are average loan size, number of loans in that branch, new loans, number of new loans, okay, total employee salaries, and what we understand is that what we want to understand is the relationship between x and y here. And why would we care about that? If we could understand the relationship between x and y, and then we can figure out how to control the cost of branches. So should we like if you knew how x and y are related, you can figure out, oh, should we reduce? So what will happen if we reduce the employee salaries? What if we reduce the total number of new loans, or what if we reduce the size of our loans, right? And if changing any of these covariates made for more profit, then that's what the bank would do, right? And here the goal is to like here is the goal is to like control this, because if the way it's thought of as control is that if you change, the management can say, okay, we figured out that the best way to make most money from this branch is to control the number of employees, or to control the size of the average loan, or the size of loans, or control how many new loans we can give, right? And so then the management can say that to the staff of the branch, that this is what we're going to do, and they can control the outputs rather than like doing what the branch would do and hoping for the best, right? So to be able to say that for the management to be able to say that, okay, let's fix these things, they need to understand this relationship. And if they could do fit a regression model, they would be able to control the operating costs. Okay, the final and the most important usage of regression is for prediction. Okay, so let's talk about an example here. So what is the prediction? So like in the example I talked about in the beginning, that if you give some dosage to someone, like a drug dosage, and you want to figure out how much pain they will like reduce, it will help the doctors later. So like let's say x is the amount of drugs, right, or dosage, or let's say the dosage of drugs, and y is the reduction in pain. If I could understand the relationship between x and y, then what if I see a new patient, okay, so let's say x is the dosage in drugs and then the age. So I have two covariates, age and dosage drugs, and based on that I figure out how after I give the so I have like many people of many different ages, from let's say like 8 to 20, and I have many possible dosages from like 0 to 7, and I give that to people. And once I collected this data and I understand the relationship how dosages work for different ages and how they reduce pains for different people, when I have a new person, and I suppose I'm the doctor and I want to decide what is the right amount of dosage for them, I could do that. I could predict. I can say like, okay, I think if you take 3 dosages, or the number the dosage of size 3, then you will have a reduction in pain in amount 2. And if I could predict that with with high certainty, then I would know what drugs to use, right? So usage of drugs generally require like good prediction. If my prediction is bad, like if I was wrong, because I didn't understand the relationship between y and x properly, then my medical diagnosis or my the prescription will not be very useful. Okay. So it's important to realize that what regression does is it studies the relationship between x and y, but it never says that x causes y. Okay. So there is a difference between a relationship and causality or causation. Right? Like, so when we say that there is a relationship between x and y, and if x increases, y tends to increase on average, it's different from saying that x causes y. Okay, saying that x causes y is a little bit more, it requires more evidence. Okay, so let's look at an example. Example of where it's clear that x and y has a relationship, but it does not imply that x causes y. Okay, so it's like in the summer, when there is so let's look at it, for example, a very simple data set that you can think of is that on the x-axis is the number of ice creams sold. On the y-axis is the temperature, or is the ambient temperature outside, right? If I look at it, so if I collect data points where I know the number of ice creams, and you'll see that there is a relationship that will be like, as the number of ice cream grows, the temperature grows. That doesn't mean the selling ice cream increases the temperature, right? There are many other factors that affect the number of sales, the temperature, and they have nothing to do with ice cream, right? So it's important to understand the difference between relationship and causation. Another example would be, so let's say x is the size of of vocabulary, okay, and y is the size is the writing speed. If you look at the data set, you will see that people with higher size of vocabulary will generally have higher writing speed. But it does not mean that if you have more vocabulary that you will write more, right? Write faster. Writing faster depends on other things like age or experience and so forth, right? So it turns out there is a variable, there are other variables like z, let's say z, which is like age or experience with a language. And other variables that affect both x and y. And that's why x and y seem to have a relationship. But it's clear that the size of vocabulary does not cause your writing speed to increase, right? So if you just learned one more word or like few more words today, your writing speed would not increase just in a day. It's just based on practice and other things, right? Age, experience, education, all these things affect your vocabulary and writing speed together. So these variables are generally called confounders, because they are confounding the relationship between x and y through these variables. The relationship between x and y that we found is accurate, but the cause of the relationship is confounded by these variables. Okay. So the strength of a relationship does not tell you anything about causation. So for example, let's look at these two data sets. Like I'm looking at two scatter plots. So let's say one scatter plot is like this, and the other scatter plot is is like this. So here you see that this the relationship here in this case is stronger, right? In the sense that there is less uncertainty in y. If I know x, I kind of know y, right? But this does not mean that if but this does not mean that there is more causality here. Okay, causality does not matter how much data you have. Okay, how many data points you observe, you will never be able to address causality with certainty. Okay, Causality is very different from regression. Regression is just trying to understand, like, okay, if I see this, and in the people I see large x's, I also see large y, or in the objects I see large x's, I also see large y. It does not mean that x causes y. Maybe there is another thing that's causing both x and y. So confounding is a very hard problem to solve. And so generally to understand, to imply causation, you have to know a lot about the process so that you can like rule out confounding. Okay. So so this is the motivation on why we want to do regression. So let's start with defining what regression is. So this is chapter 1.3, and we're going to define what the simple linear regression model is. So we say the simple linear regression model. So what is a simple linear regression model? It is first that x is just one variable, it's just one predictor. So simple is to denote that x is just one predictor. The regression curve is a straight line. Okay. So when we say simple linear regression model, we assume these two facts. Okay. So in that case, how can we write down this regression model? So we say y, the predictor, is related to x via this model. So what is beta 0? Beta 0 is the y-intercept of the regression curve. Beta 1 is the slope of the regression curve, and epsilon is the error. Okay. So so let's say we have a data set. So when we have a data set from regression, we assume that we observe many x's and many y's. So the data I will come back to this like much like more, and talk about the properties here. But let's talk about what the data set looks like. The data set for a simple linear regression is basically this. For each person, I have x1 and I observe y1. That's the first person. I observe x2 and I observe y2. And I observe x3 and I observe y3. What I don't observe is the errors. So I say, what I have is, I say y1, if there was no randomness in the data, would have been this one. The value of y1 would have been beta naught plus beta 1 x1. But since there is randomness, and that randomness is, I call that randomness epsilon 1. Okay. y2 is beta 0 plus beta 1 x2 if there was no randomness, and I have randomness in my model, so that's what the randomness is. What I observe is this, guys. Okay, maybe I should do that with green. What I observe is this, guys, here. What I don't know are these guys here. Okay, and I observe this for all the data points up to yn. Okay, so it's like if I have a scatter plot, I only observe these data. This is the only data I observe, right? This is x, this is y. I don't really observe what the true regression line is, and since I don't observe the true regression line, I also don't know what E1s are. Okay. What I assume is that these x1 through xn are fixed. Okay. What do I mean by that? So when I ask you to collect the data, this is how I go about collecting the data. I say, so like, okay, so the big assumption that I make, the first assumption I make is that x1 through xn are fixed in the data set, okay? And what does that mean? What does that mean? Let's understand that. Okay, so so when I collect the data, I say, so let's say I want to collect the data between age and bank balance. Okay. Suppose I want to understand the relationship between age and bank balance, and I just care about how age affects the bank balance. So this is X, this is Y. So I say, okay, go to the field, ask someone who is 18-year-old, 19-year-old, another 18, 19, 21, 27, 35, and 17. Okay, go to the street, ask people, ask someone who has age 18 what their bank balance is, and collect that. That's what you will get. That's the first data point. Next, find a 19-year-old, collect their income, their bank balance, and then go to another 18-year-old and collect their bank balance, and so forth, and go to the 17-year-old, collect the bank balance. So what has happened now is that these are fixed. Okay, so that's what you did. Okay, so that's what you did. I asked your friend to collect data again. Okay, friend. So what did your friend do? Your friend went to the street and found an 18-year-old and collected their bank balance, and 19-year-old and collected their bank balance, and did the same. Okay. You and your friend, for both you and your friend, the age of your participants are the same because I asked you to keep it same. What changes is their bank balances, because it will be a different person. So let's say there will be like $200 in their account. Your friend probably found one person who has like a different number, right? So you see that this part of the data is random. What is fixed is xi's. And when I say that I fix xi's, I mean that when I decide what xi's are before I go into the field, and I decide on what kind of data I want to collect. Okay, so in this class, what we will the framework that we'll study is where we'll assume that x's are fixed, and the only randomness in the data is coming from who did you ask, because there are many people of age 18, and we need to, like, since if you collected the data and if I collected the data, or if I collected the data at a different time point, I'll get different people who have age 18. The responses will be different. Okay. Once I have the data set, I will try to understand the relationship between bank balance and age, and the way I will understand that is by figuring out the regression curve, or by figuring out what beta 0 and beta 1 are. Okay. So beta 0 and beta 1 are called parameters. And for the whole point of collecting the data is to understand, to figure to know the to figure out the regression curve, and beta 0 and beta 1 play basically the basic role in when computing the regression curve, right? So I want to understand that. Okay. Y1 through yn are random, right? Because this is x1, this is x2, this is xn, those are fixed. There will be y1 here, this is y2 here, and this is yn. This is random because if different person collected the data, that's where randomness will come from. Okay. E1 through En are called unobserved noise. If I knew E1 through En, I know the relationship between y1 and x1 is this. Right? If I knew E1, I know that y1 minus E1 equals to beta naught plus beta 1 x1. And then there is a deterministic relationship between this guy and this guy. Okay? We can never know what E1s are, so we can't never understand, we can never get a deterministic relationship. The reason we have a deterministic relationship is because we don't know epsilon. Okay? And they are called noise because there is randomness, and that's why things differ, and we can't things we cannot understand or cannot summarize, we call that noise. Okay. We assume that epsilons are normal random variables. We don't observe them, but we assume that they are normal random variables. And what is the main assumption we make is that the mean of the normal random variable is 0. And that's important, okay? So we are saying overall y is like beta 0 plus beta 1, but there is a normal noise added with mean 0. Okay. We assume that expectation of the mean or the expectation of epsilon is 0, and we assume that the variance of epsilon is sigma square. Okay. We also assume epsilon 1 and epsilon 2 are independent. Okay. So we have this data set, we have our regression model, which is like y1 equals to beta 0 plus beta 1 x1 plus epsilon 1. y2 equals to beta 0 plus beta 1 x2 plus epsilon 2, and yn equals to beta 0 plus beta 1 xn plus epsilon n. So we know x1, x2, xn are fixed, so these are fixed. These are normal random variables, and these random variables have nothing to do with each other. They are independent. Right? Like the error in the first observation has nothing to do with the error in the second observation. The relationship would have been between y and x is not deterministic because these are random. Okay? If these were 0, then the relationship between, if epsilon 1 through epsilon n were 0, then the relationship between y and x would be deterministic. Okay. And how does the data set look like? The data set is basically data set is like you fix x1 through xn and you go to the field and you collect. So that's what one data set looks like. And generally you will have access to one data set here, and you will study that to figure out what b0 and b1 are, because these are unknown. Okay. So what does the observed data look like? The observed data, when we say observed data, we generally mean x1, y1, the pair of n data points. And you can plot them into the scatter plot if you want, right? These are the scatter plots. So this is the scatter plot of observed data. Okay. So since epsilon 1 through epsilon 1 are independent, what is the covariance between epsilon 1 and epsilon 2? It's 0, right? In covariance 0 means independence implies covariance 0, right? So this is because epsilon 1 and epsilon 2 are independent, right? So let's understand some properties of the regression model. So so the question is, so let's understand the properties or features of simple regression, simple linear regression model. The first property is that y1 is a random variable. Why? Because if you went and collected the first value of your response, you'll get it to be different than what if your friend did it, right? So y1s are random variables. Similarly, y2 through yn are random variables. Okay, so random variables have expectations, means, and distributions. So let's compute that. What is the expectation of y1? The expectation of y1. What is y1? Remember, y1 is this here, right? So let's write it down. y1 is beta 0 plus beta 1 x1 plus epsilon 1. Okay, what's random and what's fixed in this equation here? Fixed quantities are, fixed quantities are this, and random quantity is here. So when you add a constant to a random variable, the expectation gets added by that. So beta 0 plus beta 1 x1 plus expectation of epsilon 1. What is expectation of epsilon 1? Epsilon 1s are mean 0 random variables, right? And mean 0 with mean 0 with variance sigma square. So beta 0 plus beta 1 x1 is the expectation of x1. What about the variance of y1? That's the y1 is this formula, right? y1 can be written like this too. So if you add a constant to a random variable, the variance of the random variable is the same as the variance of a constant plus the random variable. And what is the variance of epsilon on? Sigma square. So expectation of y1. What about the expectation of y2? It's expectation of beta 0 plus beta 1 x2 plus epsilon 2. So there is beta 0 plus beta 1 x2 plus expectation of epsilon 2. Sorry. And since epsilon 2 is also a mean 0 random variable, we have that the variance of the expectation of y2 is beta 0 plus beta 1 x2 plus 0, which is just this. What about variance of y2? Is the variance of beta 0 plus beta 1 x1 plus beta 1 x2 plus epsilon 2. Since this is a constant, it's the same as the variance of epsilon 2, which is sigma square. So we see that the variance of y1 equals to variance of y2 equals to variance of yn, and that's equal to sigma square. What about the expectation of y1? That's beta 0 plus beta 1 x1. The expectation of yi for some value of I is just beta 0 plus beta 1 xi, right? Okay. So what is the covariance between yi and yj? So that's another property. What is the covariance between yi and yj? So that's the covariance between beta 0 plus beta 1 xi plus epsilon I, comma, covariance between beta 0 plus beta 1 xj plus epsilon j. These two are constants. So if you have constants in the covariance, if you did, when you did the homework, you realize that's the same as the covariance between epsilon I and epsilon j. And we know epsilon I and epsilon j are independent, so the covariance of z is 0. Okay. So y1 through yn are independent. Or at least that's what it seems like, right? It's not always, so what is the distribution of y? So yi is beta 0 plus beta 1 xi plus epsilon I. And epsilon I is a normal random variable with mean 0 and variance sigma square. So I'm adding, when I'm adding a constant to a normal random variable, what happens? So if epsilon is this, then I know that beta 0 plus beta 1 x1 xi plus epsilon I is a normal random variable with mean beta 0 plus beta 1 xi and variance sigma square. Okay. So yi is a normal random variable with just the mean shifted. Okay. So by assuming this model here, okay, or thinking about this data set here, thinking about this data set here, we have realized that there are, like, we have found out some properties of y. So we have found out that yi's are random variables, yi's are random variables, and yi's are means. These variances, they're different means but the same variances. Their covariances are 0, and we have also found the distribution of yi when we know that the distribution of epsilon I is normal, mean 0. Okay. What is epsilon I? So epsilon I. So suppose let's just look at a plot to see what epsilon i's are. So let's look at the scatter plot. Okay. So this is what x and y looks like, the scatter plot of x and y. And let's say this is the regression line that we generally would not know, but maybe we are in we are in God mode and we know what the regression line is. Then how much does this y exceed from the regression line is the epsilon I. Okay. How much this value here is below the y is the epsilon y. So in this case, epsilon I is negative. In this case, epsilon I is positive. Okay. So this is a positive value. This is a negative epsilon. Okay. So epsilon I basically tells you what the departure is, right? So epsilon I is the departure from the regression line, regression curve. And since we are in a simple linear regression model, the regression curve is just a straight line. Okay. So let's try. So what is the goal of our regression? Goal is to collect data. The ultimate overarching goal in regression is to collect data so that an estimate beta 0, beta 1 and sigma square. So what I want to talk about is what are the interpretations of beta 0, beta 1, sigma square, right? Before we learn how to estimate them from based on the data, we need to understand what beta 0, beta 1, and sigma squares represent, right? So let's try to do that. So let's try to understand what beta 0, beta 1, and sigma square mean. So let's do it through an example. So an example, let's consider the example. So you have a electrical distributor who is studying the relationship between x, the number of bits, and y, so let me see. A consultant for an electrical distributor is studying the relationship between number of bids requested by construction contractors for a basic lighting equipment during the week and the time required to prepare the bids. Okay. And y is the time required to prepare the bids. So you are some people ask for bids from you, and you have you have x is the number of bids, and it wants to understand how much time did you have to spend preparing the bids. Okay. And suppose someone told you that the model for the number of bid the time required for the bids is this. Okay. So this is the model. So that means for the ith week, if you wanted to know how much time it took to prepare the bids, you would want to use this model: 9.5 plus times 2.1 times x plus epsilon I. Okay. So that means if for the ith week xi is 45, then yi is 9.5 plus 2.1 times 45 plus epsilon I. So that's 104 plus epsilon I. So what does that mean? It means that yi is a normal random variable with mean 104 and variance sigma square. Okay. So suppose so that's what you would say. So you'd say that if for the if you know that this is the model that's true for the relationship between the number of bits xi and the time it required to prepare the bids, then you, by this relationship, you realize that if for some week there are 45 bids, you think that the amount of time it will take you to do that will be random depending on the week, right? Maybe you are in a good you're more efficient some week and you are less efficient some weeks, and but that will be a random variable, and it'll be 100, like it'll have a mean of 104 and variance of sigma square. Let's say that the data that you collected for that week, so at the end of the week you looked at the number and it turned out that it actually took you 108 hours. Okay. So then you will know that epsilon I for that week is 108 minus 104, so it's 4. Okay. Okay. So what is this epsilon I? Epsilon I is the deviation of yi from its mean. So since expectation of yi is 104 and epsilon yi was actually 108, the deviation of its mean is this. Because the random variable does not take its mean always, right? It's around its mean. So another way to see this would be via this picture. Okay. So this is how a data set looks like. You have the number of bits, right? So the electrical bit picture. So you have the number of bits and you have the number of hours on the y-axis, and the mean of y is a straight line. So expectation of y is 9.5 plus 2.1 times x, right? If you know x, the mean of y is a straight line, and that's the straight line, and that is the mean response line sometimes. Okay, it's called the regression curve, or sometimes it's called the mean or it's called the mean response line. Okay, what happens to a particular y? A particular y is distributed around this value, okay, and with some variance, and you see sometimes you'll be above the line, sometimes you'll be below the line, right? And in this case yi is here and the value of epsilon is 104. Okay, so now let's try to understand let's try to go back to our result here, and let's try to understand what 2.1 means. What is the meaning of 2.1? Meaning of 2.1 is represented here. So the meaning of 2.1. So it says that if you increase x, right, what is this line? This is the regression curve. So I'm just plotting the regression curve. On this axis, I'm plotting the expectation of y. And this is on this axis, I'm plotting x. And this is the, sorry, I'm plotting expectation of y, and this is the regression curve or the mean response curve. And since we are dealing with a linear regression or a simple linear regression, the mean response curve is a straight line. And 9.5 is its y-intercept, and 2.1 is slope. So what does 2.1 mean? It means that if you increase x by 1 unit, y expectation of y will increase by 2.1 units. So 9.5 is the y-intercept of the regression line or the regression curve. Okay, 2.1 is the slope of the regression curve. And it implies that if x increases by 1 unit, expectation of y increases by 1 unit, right? Remember, y is random, expectation of y is non-random. I can't tell what will happen to y, what will the output be, right? Because it could be above the regression line or below the regression line. But I can tell you what will happen to the regression line as I change, right? So in this picture, you see that if I increase x, the regression line moves up. The value of y is not on the regression line, it's around the regression line, right? So I can't tell what exactly yi would be, but I would be able to say that the regression line moves up. So what is the interpretation of beta 1? Beta 1 is the unit change in expectation of y when x increases by 1 unit, right? It's not a change in y, that's different, right? The change in y is random. Expectation of y, however, is a fixed quantity, and that's what we want to understand. Okay, so that's the interpretation of beta 1. Let's go back, and so let's say, what is the interpretation of sigma square? So let's understand the interpretation sigma square. So this is the line and this is the sigma square. So let's say that I have, maybe I should draw it like just like this. Now, how do I draw this? Let me just see if I can replicate this image. So this is the regression line, and I have the bell curve here, and I have another bell curve here, and so forth, right? And then you can see, okay, maybe actually, but let me draw this properly. Okay, so let's draw here, here, and then here. Okay, and now let's draw this here. Okay, and I have a regression line that's like this. Okay, so let's say, okay, and let me just erase this here just a little bit to say that it's okay. So this is my x-axis, this is my y-axis, this is the expectation of y given x. Okay, and now I know that y falls on a bell curve centered around here, right? Why can't I draw a bell curve? Because I'm not a good drawer. Yeah. Okay, so that's what x looks like, right? So I know that variance of y1 is equal to the variance of y2, and they are all sigma square. What happens? So what is the sigma square representing? Sigma square is representing how much uncertainty does y have around the regression curve. What if I double the sigma square? If I double the sigma square, then the spread around the line will be larger. So it will just become larger. Okay, so that means there will be, so what it means is that, let me just try to draw this. It's really annoying if I can't draw the other side of this picture. Okay, maybe it is a little bit here. Sorry guys. Okay, yeah, that's better. Okay, so this corresponds to 2, or so when larger sigma. Sigma square. This is smaller sigma square. So what's really happening here is, so what's really happening is sigma square represents the uncertainty around this line, around the regression line. Okay, the larger the sigma square, the more chance that y will be like really above the regression line or really below the regression line. If your sigma is small, then it will concentrate around the regression line. So let me draw some scatter plots to show you what that should look like. So like for, if I have x here and y here, and I have a regression model with very small sigma, and this is the regression line. If I have a regression model with very small sigma, this is what it will look like. It will scatter around the line, but it will be very, very narrow. If I have a same model and the same line, but larger sigma, then the variability around the line will be much larger. So where is the sigma? So this is small sigma, or small standard deviation, or small variance. This is larger sigma. And if you have larger sigma, even larger sigma, the variable will change a lot. Okay, so the certainty of how close y is to the regression line is defined by sigma. So beta 0 talks about the intercept of this regression line, beta 1 talks about the slope, and what beta 1 represents is unit change in y expectation of yi, which is the most important part. Expected change in expectation of y, when x increases by 1 unit, and sigma square represents how much uncertainty is there in the regression line. Okay. So let me hammer this meaning a little bit more. Sorry. Let me hammer this meaning a little bit more, and let me talk about what the unit. Why is beta 1 representing the change in expectation of y and not y? So, so let's look at this very simple data set. I have let's say this is the regression line, or like I don't even know the regression. Let's assume that I don't know the regression line. Okay, sorry. So let's say I have this regression data, and I have 1, 2, 3, 4. So I have a bunch of data here. So 1, 1, 2, 3, 4, 5, 6, 7, 9. Okay. So let's say this is the tree regression line that you don't observe. Okay. We only get data. We don't know. This is the regression curve. We don't know the regression curve. So when x increased, so this is x, this is y, right? I don't know what's going on, guys. Sorry. So this is x, this is y. So when x increased by 1 unit, the slope of the regression line says y should increase. When x increased from here to here, y should increase from here to here. But the value of yi that you observed is not going to be, right? It's not going to be exactly different from this. That's because this is the value of y lies around this line, but it's random. If someone else went and collected this data set where there are like 1 people with x equals to 1, 2 people with x equals to 2, and 3 people with x equals to 3, and 4 people with x equals to 4, if they collected the same data again, they will get something else. Maybe therefore their x 1, 2, 3, and 4, maybe they will get something like this. Right? So they will get different data sets from what you get. So the change in x, so when y is here, it gets still possible. When x goes from 1 to 2, it's possible that the value of y went down, or it's possible the value of y went up, right? So it could have gone up here, or it could have gone down here. But that's not the thing that what beta 1 represents. Beta 1 represents that the value of the regression line changes. So beta 1 talks about the value, change in value of the regression line. Okay. So this is the interpretation, and let's let's look at the car data set that we saw before. And in the car data set, we observed this data, we observed this scatter plot, and in the next lecture we will see in the next lecture it should be lecture 3 here. Okay. In the next lecture we'll see how we can fit a regression line. You don't know the regression line, but you can fit a regression line, and that's that. So that's how, based on the data, you can compute or you can estimate beta 0 and beta 1. And since we don't know them and we estimate them based on data, we call them beta 0 hat and beta 1 hat. And once we have that estimate, we can plot the line and we can understand or interpret this line. Okay. And the interpretation will be basically like beta 1 hat means the unit change in x, talks about estimated change in the regression line, right? Okay. So that's what we will do next class. Now that we know what the meaning of beta 0, beta 1, and beta sigma square are, we will collect data and we'll estimate them. But before we do that, we would want to talk about what kind of like data sets can we collect. So there are two major kinds of data sets for regression. Okay. The first is called the observational data, and the second is called experimental data. Okay. And the reason we are collecting the data set is because we don't know what beta 0 and beta 1 are, and we want to understand that relationship. Okay. And as we talked about, like, linear regression seems like a nice model because it approximates things well. Okay. What are observational data? Observational data are data where we can't control the value of x. Maybe for ethical reasons, maybe the data was collected before and we had no hand in collecting the data, or maybe there are other things that can happen, and that's why we couldn't choose the value of x that we want to. So it's like observational data is data where I can't be like, okay, go find the height of people for who are aged 17 and then 18 and 18 and a half and 18 and 3/4 and so forth. Observational data is the data that already exist and that was collected because like observational that you couldn't control the value of x. So for example, you could say like, let's look at the age of x be the age of cancer patients at the University of Florida hospital, right? So you don't control that. It's like just it's the nature process in nature decides what x are, and you just take them. Okay, so like maybe you want to understand the efficacy of chemotherapy on people, and you want to understand the relationship between age and efficacy of chemotherapy. And so age and efficacy of chemotherapy for cancer patients. So you can't just go around and be like, okay, I want to look at a 17-year-old person who is a cancer patient and who will have chemotherapy, right? Maybe this particular type of cancer only happens to old people. So what it means is that x is not chosen by you. X is already chosen, right? And then you want to study this relationship between x and y. And in these cases, since x is not chosen by you, you can't really say anything more than a very simple statistical relationship, right? You can't make causal observation about the data, right? Maybe maybe there, suppose so like a way to see this would be, let's see that there are like you are talking about the efficacy of chemotherapy versus age, and you collect a lot of data set, and you collected a bunch of people here, and all of them are like between age and 40 and 80, and then there is one patient who is at 18. Okay, and if you want to study the chemotherapy, you see that as the age increases, the efficacy of chemotherapy goes down overall, but like that. But for this 18-year-old, the chemotherapy was not very effective. Does that mean that for younger people chemotherapy doesn't work? Or does that mean that this 18-year-old had this cancer because they had some other underlying issues, and that's why the chemotherapy didn't work, right? So when you have observational data where you don't control what covariates you have or what the values of the covariates, then it's harder for in general to talk about make causal conclusions. Okay, so whenever regression analysis is done on a observational data, we only do it for descriptive properties, like to understand the relationship, not to provide causal relationship, right? So if you saw that, and you saw that, okay, for 18-year-olds chemotherapy doesn't work, but for 40-year-olds it works better, that doesn't, you should not suggest that, okay, for young people don't do chemotherapy if they have cancer. It might just mean that the people who have cancer when they are young might have other underlying issues, right? It's nothing to do with age. There are other confounding variables, right? And experimental data are very common in medical field because it might be unethical to provide like low covariate, like low dosages. Like it might be unethical to provide choose variable values of X. So let's say when they were doing the Ebola studies, right? Uh, so if you want to understand the relationship between dosage value and their treatment outcome, like whether they're feeling better or not, you couldn't decide the dosage value based on so that you can collect data in a nice way. You would the way that the way that you would collect the data is, you would be like, okay, you will be outside the doctor's office and you'll be like, okay, the doctor saw the patient and they figured out that, okay, this is the right amount of dosage for them, and then you can observe their outcome. You are not going to tell the doctor, okay, let's give this person half a dose and let's give this person 3 doses, because that's unethical, right? The goal of the doctor is to take the best guess that the best amount of doses the patient should get. And in those cases, it's a little bit hard to understand the relationship between to understand the causal relationship between dosage and outcome. So then what will be the causal relationship? The causal relationship will be like higher dosage higher dosage was the reason that the patient is doing better. That question, to answer that question, observational data are not generally very good. And the gold standard to answer causal questions, the gold standard to answer causal questions is experimental studies. Experimental data. What's an experimental data? Experimental data is more common in like fields like chemistry. So where you can control the amount of a substance when you are doing the experiment, and you want to study the output, right? Like suppose you have a X and you want to study the impurities by the change in amount of impurity in Y, or in the output when you change X. And here you can change the values of X as much as you want, the way you want it, and you can control for other variables, right? You can say like, okay, I will make sure that everything else is the same and I will change X just by 1. And if you can do that, then you can answer causal questions. Okay, so since in experimental studies you can change a covariate while keeping everything else fixed, they can be used for causal they can be used to for answering causal questions. So the reason you couldn't do that in observational studies is because when you look for different X's, you cannot guarantee that the other covariates are the same. But in a experimental study, you can, since you are controlling the values of X, you can change the value of X while keeping the value of other covariates constant. And then if Y changes, then you know the change is due to change in X because everything else was kept constant. And that will lead to like answering causal questions. So next time I will talk about lecture. This will be the lecture part 4, where we'll talk about how can we estimate beta 0, beta 1, and so forth.